Hi everybody, today we're going to be talking about atomic structure and how that relates to both physics and chemistry, because this is one of those areas where physics and chemistry really do some overlapping. So the idea today is that we'll be talking about atoms. So the first people to propose this idea of atoms were the Greeks, so this idea of atoms has been around for a really long time. And the word atom means it's something, you have something that can't be split. And what the early Greeks believed is that you had that atoms were the simplest parts of matter. Leucippus and Democritus, well, they were the first really philosophers to come up with this idea of proposing atoms, that you had matter that couldn't be split. On the flip side, Aristotle actually was somebody that didn't think that atoms were correct, that it wasn't the right way to talk about the structure of atoms. So this idea of atoms have been around for a really long time, and that's where we need to pick up at. Whipping along a few thousand years takes us to John Dalton. He was actually an English chemist. And his idea was that, atoms were the building blocks of matter. And he actually came up with a theory of atoms that says that basically atoms of the same type were the same and atoms of the different types of elements were going to be different. So saying that a carbon atom and gold atoms were actually going to be different things. You can go into a lot more explanation on Dalton's atomic theory, but for right now, basically Dalton just says that atoms are the things that actually make up matter. Whipping along even farther, another almost 100 years takes us up to the structure of what atoms are. So where Dalton said that atoms make up matter, J.J. Thomson was actually the first person to discover a part of something that makes up the atom. So in 1897, J.J. Thomson actually discovered the electrons. What he found is that they were very small in mass and that their charge was actually going to be negative. So what Thomson proposed or hypothesized was that if there has to be some negative charge there has to be some positive charge as well. And from that, Thomson came up with this plum pudding model of an atom, which was basically just a sphere that had negative charge embedded in positive charge that was going to be there. So at this point, there's no positive particles. There's just a bunch of positive charge that's going to be there that's going to take up the rest of the mass. A few years later, a fellow by the name of Ernest Rutherford actually came up with this idea of proposing that there was going to be a nucleus. And what he did is he actually shot something called alpha particles at gold foil. For that reason, the experiment was called the gold foil experiment. And what he did is he shot alpha particles at gold foil. So here, along this line, you can see that there's a beam coming out of here. The beam was actually invisible. You really couldn't see it, but the beam is for illustrative purposes. But what happened is these alpha particles, which were positively charged particles, would come shooting out of here, hit the gold foil, and a lot of them bounced off at a lot of different angles. What Rutherford believed is he really thought that these particles those alpha particles should be going right through the gold foil, because he knew that they were positively charged, knew that they were pretty darn big. What happened is as they were bouncing off, that was really a surprise to Rutherford and his cohorts in crime, Geiger and Martzen. But it was so much of a surprise that Rutherford said in a paper it was almost as incredible as if you fired a 15-inch shell at a sheet of tissue paper and it came back and hit you. So firing a shell would be like firing a bullet at a piece of tissue paper and having it bounce back. So from these conclusions, since the positively charged alpha particles were bouncing off of something in the gold foil, most of them were going through, but some of them were bouncing off, there had to be something really positive and dense that had to be inside of that gold sheet. So that allowed Rutherford to come up with a model of an atom around 1903, where Rutherford actually had a nucleus. So when you think about Rutherford's model of an atom, it looks, something along these lines here. You got a positively charged nucleus in the middle, and then you have negative electrons that are going to be around the outside of it. So Rutherford's model of an atom is actually a nuclear model of an atom with a positively charged nucleus in the middle. So that worked well, but not well enough. So in 1903, Niels Bohr actually proposed another model of an atom. It was an orbital model of an atom, as it's sometimes called, but you have the nucleus in the middle. So it's still sitting right there, and you have these electrons in these orbits, almost like planets that are going to be outside of the nucleus. The electron is able to be moving in those orbits, but it can also change position. So it could be at its position right here. It could move out to another one or another one, but it couldn't exist in between there. So what this is sometimes called a quantized model of an atom, because the electrons can only be in specific places, or more accurately, have specific energies. But as with most models, Bohr's model of the atom wasn't correct enough, and they needed to keep being reinvented. So a fellow by the name of Erwin Schrödinger in 1926 actually took the idea of an atom and made it a little more complicated, made it more mathematical, and really turned it into a probability structure. So rather than having electrons following orbits, you can have places where there's going to be higher probabilities. So this image that you're seeing here on the side is really showing where you're having a probability of having electrons, and the bluer the density is going to be, that means you have a greater chance of actually finding electrons. Now, sometimes Schrödinger's model is called an electron cloud model of an atom, and that's just a better representation of where electrons are going to be at. So a lot of times we talk about atoms, we talk about the probability of where things are going to be existing when we're actually dealing with the electrons. So what's been missing so far is actually the nucleus, and it wasn't until 1932 when James Chadwick actually discovered the neutron. It was the last one to be discovered because the charge of a neutron is neutral, which is how really the protons and the electrons were discovered. So it really did take a lot longer to discover the neutron that was going to be present in the atom. So you know that the nucleus is going to have the protons and the neutrons, and the electrons are going to be outside of that nucleus in really an electron cloud. So to talk a little bit more about the structure of the atom, we're going to go back to Bohr's model of an atom. Although it is a simpler model of an atom, it's a good model for understanding how atoms are actually put together. So one of the things that's kind of cool, and you've actually seen this before without actually probably knowing it, is that different atoms actually give off a very, very, very specific spectra that's going to be there. So the top one here would actually be what hydrogen would look like if you looked at a hydrogen light, and you saw the colors of light that are there. Hydrogen light's actually kind of a purpley color, but it's actually made of a lot of different colors that make it up. Neon is actually an orange light, but that orange light actually has a lot of different colors that make it up. You would have seen this if you've ever seen a neon light. A neon sign is actually made of neon gas that has a really high voltage that's going to be passed through it. So what happens is that these different atoms are going to be gaining and losing different amounts of light because, as we talked about before, when you have these different colors of light, they obviously have different wavelengths, they're going to have different frequencies, and in turn they're also going to have different energies. So really these spectras are like the fingerprint for a given element. So how Bohr was explaining this is basically he was saying that you're going to have atoms that are going to be gaining energy and they're going to be losing energy, and the electrons are going to be moving. They're going to be gaining and moving and changing the amount of energy that they have. So the term that they use is the term jumping. So behind me here I have a little drawing where you'd imagine a Bohr model of an atom. So you have a nucleus in the middle, and you have these orbits, or more accurately to be defined as orbitals, that the electron can be moving to. So right now we have the first energy level, the second, the third, and the fourth, or the second, third, and fourth orbits that are going to be present. But what Bohr says that electrons can gain energy and move up to a higher energy level. And every time that moves, that takes a certain amount of energy that has to go in. But then the electrons can also go back down, and when they go back from a higher orbit to a lower orbit, they're actually going to be losing energy. And when they lose energy, they can give that off as light. So really when atoms are gaining and losing energy, the electrons are the things that are changing their positions, and that change that we see is what we perceive as light. Something like that you might have seen before is if you ever watched a fireworks display, the light that's given off from the fireworks, or when the atoms are gaining energy, the electrons are moving to a higher energy level, then they lose the energy and they come back down to a lower energy level. So those colors you see in fireworks are really just coming from the gain and loss of energy that the atoms are gaining in the fireworks. Now what we call that, the changing of the positions, is something called an excited state and a ground state. So the ground state is when you have electrons at the lowest possible energy level. So if you have your electrons down here in the lowest energy level they can be in, that's something we call the ground state. And truly atoms are most often at a ground state because you're generally not seeing things give off light. You have electrons at a lower energy level. So anytime you have your electrons as close to the nucleus as they can be, that's the ground state. When they move higher to a higher energy level, there's something called an excited state. Real scientific terms there, I know, but that's actually what they're called. They're called ground states and excited states. So if you take an electron, you move it from the first energy level and you move it all the way out to the fourth, it's actually gained energy and it's become excited. But when you see the light is when the electrons move down from that farther energy level back down to a lower energy level. As it turns out, electrons moving to the second energy level are the ones that we can actually see as light. But anyway, we have ground state and excited state electrons, and that comes from gaining and losing energy. So how do atoms absorb energy? Well, they can absorb it from electricity. They could absorb it from heat, or they could also absorb it from some other types of light. So electrons changing energy levels really just comes from some particular way that the atoms are going to either gain or they're going to be losing light. We'll talk about that a little bit more later on, but it is important to understand that atoms can definitely gain and lose energy, and it's one of those fundamental ideas to the structure of atoms and to also our understanding of the atomic structure that's going to be present in atoms too. So where this all comes from, and hopefully this can tie this all back together, is into this probability of understanding how electrons exist. Now granted, it's simple with a Bohr model of an atom to draw an atom when we have these little orbit spheres that are going to be around it. But in reality, when we express atoms, it's better to be expressing them in terms of probability. So what happens is that we really get these orbitals that are going to be existing. So atoms, rather than existing in having orbits around them that electrons are in, they're actually existing in orbitals. So if you've ever taken some chemistry and looked at the way that atoms are going to exist, we sometimes write things called electron configurations, and those go right along with these orbitals right here. So the nodes and antinodes that we look at in terms of waves are something that allow us to understand how these different orbitals are going to be existing. So as it turns out, in this first energy level, you can actually have these s orbitals. So in that first energy level, it's really just a spherical orbital around it. In the second, you can have s's and p's. In the third, you can have s's and p's and d's. And out in the fourth, you can start to get s's, p's, d's, and f's. So it gives a little bit more complex drawing of how, or a complex understanding of the probability of where electrons can be existing at when you're actually having them around electrons. We're having electrons around atoms. I apologize for that. So where those come from is actually from one of Schrodinger's equations. So it's a really complicated bit of math, but the point of Schrodinger's equation, it deals with probability. So if you ever see a probability equation, this is actually what it is. But simply put, Schrodinger's equation deals with the law of probability. So when you're dealing with probability, that's really what we deal with when we deal with the electrons and the structure of atoms around it. Is that really everything that we're dealing with the electrons has a chance of where it's going to exist at. So just like here, if you look inside of the dryer, all those clothes are nicely folded. Well, at some point, you should open up your dryer and you should be able to see all the clothes folded nicely in there. Is that probably going to happen? Probably not, but there's still a chance that it's going to happen, and that's really what probability is telling us. Just like there's a chance of knowing where electrons are going to be existing at, there's a chance that we should know that our clothes are always going to be folded when we take them out of the dryer. However small of a chance that is actually the way that things are going to exist. Okay? So keep in mind when we're talking about where electrons are existing at, we're talking about how they're going to exist in these different orbits, which in reality can work as orbitals. And those orbitals are going to tell us of where we have a really high probability of actually finding electrons at. One of the places you may have actually encountered seeing light coming out of a device is something called a laser. We saw that in one of our videos. I used a laser to show light. But laser stands for a light amplification by the stimulated emission of radiation, which is just a fancy word for saying that you're giving atoms energy so that the electrons can jump from their lower ground state up to an excited state and back down and then give off the light that's going to be present. So think about laser. If you ever have seen a laser, if you think about a laser, what it's doing is just giving off light because those atoms are gaining and losing energy. And here we have a cat that always is excited to see laser dots. One other place where you may have seen atoms giving off energy is something called fluorescence. So you have fluorescent markers. Well, what's really just happening there is you have atoms that are gaining energy, and then they're giving that energy off to lower the energy of the electrons, and they give them off as something that's called fluorescence. So lots of different ways to look at atoms and the structure of atoms and the electrons around them. So if you have any questions, please let me know.